So now we're going to introduce a new term called the implicit function, which is in contrast to what we have been typically dealing with, which are explicit functions. And so an explicit function is the typical function that we've been working with, something like f of x equals 3 sine x plus 2x squared, where we have one dependent variable, our variable f, expressed in terms of one independent variable, our variable x, where we choose a value of x, and as we change the value of x, we get a range of different values for f. On the other hand, we are now going to start talking about implicit functions as well. And implicit functions are not typically going to be true functions. It's really just another name for a relation, which is a term that you've probably used when you talked about the definition of a function in your pre-calculus classes. And one of the important features of implicit functions is that they can have multiple variables. And so some examples of explicit functions: f of x equals 3x squared minus 12, y equals 2x minus 1, y equals 3z minus 4z squared. Again, it's all about this notation where you have your more complex expression on this side, and really you just have one variable on this side. So you plug in values on one side of the equation, and then you end up with a value for the other variable. Examples of implicit functions: we might have 4 equals x squared plus y squared, 3xy minus y squared equals 7, or something that doesn't even involve x and y, pi r squared h equals v. And so we're going to start using implicit functions, and I want to just talk about why we do this. First of all, some functions look nicer when they are expressed implicitly. And this could be seen in many equations. One example is the equation of a circle. 4 equals x squared plus y squared, which is the implicit form. Very succinct, very direct. On the other hand, if we were to use some algebra to write it in explicit form, we would have to express this single equation of a circle in actually two separate explicit functions. Furthermore, it involves a square root, which people don't tend to like, and I know if I can avoid using a square root, I will avoid using a square root. Furthermore, some relationships can only be expressed implicitly. So we might have an equation 3xy minus x squared y plus 2 equals xy squared. So in this case, for most people's purposes, there's no explicit form. I actually don't know that 100%. There might be an explicit form, but it's probably not something very easy to find, and I don't even want to spend the time to find an explicit form. And so we are going to leave it in implicit form. And finally, there are also just many well-known formulas that we already know in implicit form, and we don't want to have to modify them or rewrite them. And some of these equations: the equation of a circle, r squared equals x squared plus y squared; the equation for kinetic energy, energy equals 1/2 mv squared; the ideal gas law, PV equals nRT; and the volume of a rectangular prism, V equals length times width times height. These are just a few examples. There's many, many, many more. And we want to be able to apply the calculus that we've already started learning and find rates of change and derivatives for a whole range of different real-world applications that might use any of these formulas. And so that's what we're going to be moving into in the next couple of weeks.